Okay, the supercell storm, the other type that causes lots of problems for us. In this diagram here, and in the radar image on the right-hand side, we'll talk about the different features that we are looking at. The corkscrew type yellow feature that you see is the representation of the updraft that's within this storm here. And what separates the supercell storm from the other types of storms is the fact that the updraft literally rotates. It spirals upward into the atmosphere. It develops generally very strong updrafts, and in some cases extreme updrafts, where the wind speeds going upwards might reach in excess of 100 miles an hour. And the faster that wind goes up, the larger the hailstones it can hold aloft before they come down to the ground. And so in those cases where you have 100-mile-an-hour updrafts, you may be producing baseball to softball size hail. Now that's something you necessarily can't see in looking at the sky, and that's something you necessarily can't see in looking at the radar either, unless you're very good at determining what to look at. But the problem is unless you have GR level X data, you are not going to be able to see the storm tops, and that's only the only way you can really determine how strong of an outflow you might have with the storm. But getting back to the more basics though, again, here is your updrafting. You're usually finding the rear side of the storm, and around here, since most of our warm and moist air comes from the Gulf of Mexico or from the south, this inflow side is usually in the southwest portion of the storm. Now, as that air rises upwards, it's encountering stronger and stronger wind aloft. And as a result of that, that updraft that's trying to build upward into the atmosphere is getting tilted forward with height because of that increasingly strong wind pushing on it. When that takes place, all the precipitation is being carried aloft by that updraft. Once it reaches a point where it can't hold all that precipitation aloft, it begins to fall out. And because it's tilted forward with height, it's falling at a location separate from where the updraft is at, which is important because if we're falling straight back down on the updraft, it would literally be choking the life source of that storm, which is the updraft. And so that tilting forward with height is an important component of a long-lived storm. And that's what this blue downward arrow represents, is the downdrafting that's occurring in the forward portion of the thunderstorm. We call it the forward flank downdraft. From the radar perspective, it's this very broad forward portion of the storm that's both the greens, yellows, and reds. Kind of like a very large comma head. That is the forward flanks of a storm. And within that, a lot of rain, maybe hail embedded, wind all coming down to the ground and causing a lot of havoc down at ground level. Now I shouldn't say that necessarily because some folks might be raining hard and maybe only blowing 20 miles an hour. And other folks might be raining really hard and blowing 60 miles an hour. Or at your location it might be blowing 20 miles an hour now and 40 miles an hour the next minute and 20 back the next minute and 80 miles an hour the next. So there's a lot of variation in what you'll experience as you are passing through this forward flank downdraft precipitation and wind area. Notice the overall look on the radar, very broad forward portion narrowing to a tail that has this hook shape in it. That hooking shape is the result of that counterclockwise circulation that's occurring back in the rear end of the storm. This thunderstorm essentially becomes a miniature low pressure system. The low pressure center being that hook echo region. That low pressure center being the area where air is coming inward and spiraling upward. The location from which tornado development would occur if there is going to be a tornado occur with this storm here. You also refer to it as a mesocyclone. Meso meaning small, small cyclone. Miniature low pressure system is what that thunderstorm is. Notice also in the case of the supercell, you have two downdrafts occurring. The blue one in the forward flanks with all this heavy precipitation, and this red one back here, which in this case of the classic supercell thunderstorm is occurring in a relatively rain-free area. Now what's happening in this scenario is you've got, again, this strong wind at all altitudes through the depth at which this storm is building upward. A lot of that wind that's impacting the backside of that storm is going to be acting like a rock in a stream. And so you've got air that's flowing around that storm, and up at high altitudes where it's extremely strong is stretching that cloud mass well downstream. That's what you're looking at here. And this may be 50, 100 miles, 200 miles on downstream of where the updraft is taking place at. But some of that wind that's impacting the rear end of that storm literally comes down its backside. And when it comes down to the ground, it spreads outward in all directions, and some of that air gets wrapped up into the updraft of the storm. Now notice the location of where your tornado occurs. It's actually underneath the tallest part of the storm tower, back in the rear end of the storm, usually on its southwest side. So that's where tornado formation takes place. Relative to the radar, it's going to be taking place right inside that black circle that we showed there. That again is the low pressure center, that's the mesocyclone center, that's the area where lower cloud-based formation occurs. We call it the wall cloud. And from that wall cloud, if everything is just right, a tornado may form from that. So these are the elements that we look at when we're looking at a supercell thunderstorm. And this is the look of it on radar. In this video that you watch here, you can kind of see the upward spiraling, especially in this component right over here. How this air is not only lifting upward, but it's spiraling. And the result of that, or the reason for that, is that you have this increasingly strong wind with height, and that wind is changing direction with height. From a southeast wind near the surface to southerly near cloud base to southwest at mid-altitude and up to a westerly wind by storm top. And so this changing wind direction with height is what helps to set up a large-scale horizontal rotation, which the thunderstorm's updraft will physically tilt from the horizontal up into the vertical. And that's where your rotation comes from with this storm. Here's the normal leveling off point. We refer to that as the anvil. The air is stable above that point. We'll talk about that a little bit more in just a moment here. Again, idealized diagram on the left and the radar image on the right-hand side, and note the locations of flow boundaries. In the case of the supercell storm, you've got two outflow boundaries, two shelf clouds taking place. You've got one occurring on the lead edge of the storm, ahead of the forward flank downdraft. You also have a rear flank downdraft shelf cloud back here as well. And so you can see that depicted on both of these. This in-between segment here is simply a cloud boundary that separates the warm and moist air from the south side feeding into this mesocyclone's low pressure center from the rain-cooled air that's on its north side. You can see the arrows showing the direction of wind flow around that particular structure there.